For as long as we've looked up at the sky, one constant has defined our world, the moon. Our single, steadfast companion, circling us in perfect rhythm, a reminder that in the vastness of the cosmos, Earth was never entirely alone. Its glow pulled the tides, shaped our calendars, inspired myths and science alike. The moon was the familiar presence in a universe that changes endlessly. And for centuries, we believed it was the only one. The one and only natural satellite of Earth. Except now, it isn't. Something small, quiet, and invisible to the naked eye has joined our planet's journey through space. Astronomers scanning the night sky in late 2025 detected an object whose motion didn't match any known asteroid, comet, or piece of debris. It wasn't racing past on a hyperbolic trajectory, and it wasn't circling Earth the way our moon does. Instead, it seemed to drift beside us, locked in an invisible harmony. They named it 2025 PN7, a designation that might sound unremarkable, but the orbit it traces around the Sun tells an extraordinary story. From our perspective, it looks as though the object loops around Earth, sometimes ahead, sometimes behind, weaving a slow, intricate pattern through the stars. But this illusion hides a deeper truth. 2025 PN7 doesn't orbit Earth at all. It orbits the Sun just as we do. Yet the two paths are so astonishingly similar that the asteroid and our planet remain in sync, bound not by direct gravity, but by geometry, resonance, and chance. Astronomers call this rare configuration quasi-satellite motion, a gravitational dance so delicate that even the smallest push could end it. To understand why it matters, imagine two dancers moving around the same stage at nearly the same speed. From far away, their steps seem choreographed, their timing perfect, their motions intertwined. But in truth, each follows their own rhythm, their own circle. Gravity doesn't chain them together, it merely aligns their tempo. That is what's happening now, here, between Earth and a rock barely 60 meters wide, drifting millions of kilometers away. NASA's Orbital Dynamics team ran simulations, calculating how this new companion moves and where it's headed. Their models reveal that 2025 PN7 has likely been near us for decades, maybe longer, hidden among the countless near-Earth objects that pass unnoticed each year. And it will remain here for decades more, until about the year 2083, when the subtle tug of other planets, the pressure of sunlight, and the whisper of time itself will finally nudge its orbit away. For the next half-century, Earth has what some are calling a second moon. The term isn't technically correct, but it captures the wonder, because although this object isn't gravitationally bound to Earth, it shares our journey. It travels beside us, tracing the same celestial highway, keeping pace like a silent companion in the endless night. In a sense, 2025 PN7 represents everything we love about science, the way it transforms the ordinary into the extraordinary simply by noticing, by paying attention. A faint dot of light becomes a story about the precision of gravity, the resonance of orbits, the clockwork of the cosmos. And like every great story in science, it begins with curiosity, someone asking why this tiny speck moved differently than expected. The discovery came from a network of automated telescopes sweeping the skies each night, systems designed to find and track near-Earth asteroids. They take image after image, hour after hour, comparing frames to spot anything that shifts against the fixed background of stars. When they find something moving, it's flagged. Most of the time it's nothing special, an already known asteroid, a small rock making its routine pass, or even a piece of old space debris reflecting sunlight. But occasionally, the algorithms catch something strange. In late 2025, one of those systems, an array in the southern hemisphere, detected a faint, slow-moving object. Its motion didn't fit any predicted orbit. It wasn't fast enough to be an asteroid in a typical flyby, and it wasn't slow enough to be a satellite. The tracking software flagged it for human review. Within hours, telescopes across the world turned toward the same patch of sky, and what they found astonished them. Night after night, 2025 PN7 followed a path that seemed locked to Earth's motion around the Sun. Every observation refined its orbit, and every new calculation confirmed what the first data had suggested. The object's period around the Sun was almost identical to Earth's, just about 1 year. It wasn't circling us, but it was staying with us. A companion, not a captive. At first, the team hesitated to label it. Was it a Trojan, a co-orbital asteroid, a horseshoe object? These categories describe subtle gravitational relationships that occur when small bodies interact with planets. But 2025 PN7 didn't fit neatly into any of them. Its relative motion, when plotted from Earth's frame, drew loops, tight spirals, figure eights, graceful arcs that returned again and again. This was no Trojan trailing in our orbit, nor a simple co-orbital. This was something rarer, a quasi-satellite. From our vantage point, it might appear to orbit Earth once per year, tracing a backward retrograde path across the sky. In reality, both Earth and the asteroid are circling the Sun, side by side, like two runners on parallel lanes of an invisible track. Sometimes one is slightly ahead, sometimes behind, but their overall rhythm remains the same. It's an illusion of companionship created by celestial mechanics, and yet a real one. That illusion becomes even more vivid when you imagine what an observer on the asteroid would see. Looking up from its rocky surface, Earth would appear as a bright blue world suspended against the black, moving slowly back and forth over months and years, never straying too far. To a creature living there, it would seem as though Earth were their own moon, an enormous presence dominating the sky. The truth, of course, is reversed. They are the wanderer, and we are the home. But perspective, as always in space, is relative. The asteroid itself is tiny, no more than a fragment compared to our moon. Based on its brightness and reflectivity, astronomers estimate it to be between 20 and 60 meters in diameter, about the size of a large house or a small building. Too small to see with the naked eye, but bright enough to be tracked with modern telescopes. Its rotation, composition, and surface properties remain largely unknown. But its orbit, that elegant rhythm it shares with Earth, is now mapped with precision. The mechanics behind such motion are subtle but beautiful. Everything in the solar system orbits the Sun according to Kepler's laws. Each orbit has a semi-major axis, the average distance from the Sun, and an eccentricity, a measure of how stretched the path is. Earth's orbit is almost perfectly circular, with a semi-major axis of 1 astronomical unit, about 150 million kilometers. 2025 PN7's orbit matches ours so closely that both complete a revolution around the Sun in nearly the same time. But there are differences. Its path is slightly tilted, a few degrees inclined relative to Earth's plane. Its orbit is also a little more eccentric, meaning it moves closer and farther from the Sun during its journey. These small variations are what create the looping effect we see from our perspective. When the asteroid moves slightly faster, it drifts ahead of Earth. When it slows down, it falls behind. Gravity does the rest, nudging it back toward the balanced configuration that keeps the two near each other. It's a fragile harmony. Over decades, tiny perturbations from the Moon, Venus, Mars, and even Jupiter accumulate. Solar radiation pressure, the push of sunlight itself, adds subtle acceleration. Together, these forces slowly distort the orbit until eventually the quasi-satellite pattern collapses and the object drifts away. That's expected to happen around 2083. Until then, we live in a rare moment in astronomical time, a chapter where Earth and a small wandering stone share the same path around the Sun. Two travelers bound not by gravity, but by coincidence. Two worlds, unequal in scale, yet synchronized in motion. And when we realize that, the question arises, what does it mean for a planet to have a companion not truly its own? Is this a second moon, a cosmic illusion, or simply another reminder that in the vast machinery of the solar system, nothing ever moves entirely alone? Because perhaps that's the point of 2025 PN7, not to redefine what a moon is, but to remind us that even in the predictable order of the cosmos, there is room for surprise. When scientists first confirmed that 2025 PN7 was moving in quasi-satellite motion with Earth, the announcement rippled quietly through the astronomical community. It wasn't front-page news, but for those who study orbital mechanics, it was electrifying. Because hidden inside that small, faint object was an exquisite natural laboratory, a living demonstration of how gravity weaves temporary partnerships between worlds. From the outside, quasi-satellite motion looks simple, but inside the equations, its chaos delicately balanced by mathematics. Imagine two gravitational wells, one from the Sun, one from Earth, pulling on the same small object. Each tug modifies the other, producing an orbit that is neither around Earth nor around the Sun alone, but around a constantly shifting point in space defined by both. That's why 2025 PN7 appears to orbit Earth in reverse, tracing a lazy loop that repeats year after year, even though it's really following its own solar path. To visualize it, picture the two cars on a racetrack again, Earth in one lane, the asteroid in another. Both complete a lap around the Sun every 12 months, but one car drives slightly closer to the center of the track, the other slightly farther out. The one inside moves a bit faster, the one outside a bit slower. Over time they drift, then realign, their relative positions shifting in a graceful oscillation. To an observer riding in the faster car, the slower one seems to move backward, drawing loops that repeat endlessly. That optical illusion, born from simple orbital geometry, creates the appearance of a second moon. Astronomers plotted the orbit over centuries, both backward and forward. They found that the relationship between Earth and 2025 PN7 is remarkably stable for a body so small. It may have entered this co-orbital configuration decades ago, perhaps in the early 1970s, long before anyone had the telescope sensitive enough to see it. And unless disturbed by a major gravitational encounter, it will stay here for roughly 50 more years. After that, subtle shifts in the orbit, tiny nudges from Venus and Jupiter, will pull it away. It may transition into what's known as a horseshoe orbit, tracing an enormous arc that approaches Earth from one side, swings around, and retreats to the other, repeating over centuries. That slow evolution is part of what makes quasi-satellites so scientifically valuable. They occupy a middle ground between the familiar and the exotic, neither permanent moons nor passing asteroids, but temporary companions shaped entirely by resonance. Each discovery refines our understanding of how small bodies move through the Sun's gravitational field, and how planets like Earth influence them. NASA's simulations show that 2025 PN7's semi-major axis is almost exactly 1 astronomical unit. Its eccentricity, how stretched its orbit is around 0.02, slightly more elongated than Earth's. And its inclination, the tilt relative to our orbital plane, is just a few degrees. Those parameters place it inside a narrow corridor of dynamical stability, a region where the combined gravitational forces of the Sun and Earth can hold it in quasi-satellite motion for decades. For planetary scientists, this corridor is fascinating. It's a glimpse into the invisible architecture of our solar system, zones where objects can linger, balance, and sometimes switch between modes of motion. The transitions between quasi-satellite, horseshoe, and Trojan states aren't random. They follow predictable pathways governed by resonance, each like a different rhythm in a cosmic symphony. Studying those rhythms helps researchers refine the long-term stability models used to track asteroids and plan missions. That brings us to a question many space agencies are now quietly asking. Could 2025 PN7 become a target for exploration? Its proximity to Earth makes the idea tempting. The asteroid's orbit keeps it relatively close to our planet, though close in astronomical terms still means millions of kilometers. But compared with the main asteroid belt, it's right next door, Reaching it would require far less energy than traveling to Mars or Jupiter's moons. In principle, a small spacecraft equipped with ion propulsion could rendezvous with the object, map its surface, maybe even collect a sample. Why bother? Because quasi-satellites are windows into time. They might hold material as old as the solar system itself, untouched, unheated, unaltered. Studying them could reveal how the early solar nebula condensed into planets, and how small bodies interact with larger ones over eons. Some researchers even speculate that quasi-satellites could serve as natural waypoints for future missions, stable, predictable stepping stones in near-Earth space. But there's also a more philosophical reason. Visiting 2025 PN7 would mean visiting a cosmic companion that for now shares our path, a body that travels with us not by capture or control, but by coincidence. It would be like meeting another traveler on a long road, someone who has been beside you the whole time, unseen in the dark. The asteroid itself is faint, about magnitude 21, barely within reach of large amateur telescopes. To photograph it, you need long exposures and precise tracking. Each frame shows a tiny streak against the star field, proof of motion in a universe that otherwise seems still. As data accumulates, astronomers refine its orbit, adjusting predictions, watching how sunlight and planetary tugs shift its path by fractions of a degree. Every observation is a conversation with gravity itself, and the more we watch, the more we see patterns. The asteroid's motion isn't random. It breathes in sync with Earth's orbit, an echo of our own revolution around the Sun. When Earth moves slightly faster, the asteroid drifts behind. When we slow near aphelion, it creeps ahead. The two are locked in rhythm, a dance choreographed not by design, but by physics. Some have compared quasi-satellites to musical harmonics. Just as two strings vibrating at nearly the same frequency produce beats, soft pulses that fade in and out, so too do Earth and 2025 PN7 create gravitational beats, cycles of alignment and separation that span decades. The resonance keeps them near each other without requiring permanent capture. When that resonance fades, the music ends and the asteroid drifts away. If you could stand on its rocky surface, you would see Earth as a brilliant sapphire sphere, rising and setting over months rather than hours. The Sun would trace the same familiar arc, but Earth would hang nearby, sometimes ahead, sometimes behind, never vanishing completely. For generations of humanity, our sky has held one moon. From 2025 PN7's sky, there would be two, the Sun and the shining blue planet it follows. Back on Earth, telescopes continue to watch. Every few months, new data refine the orbital model. The International Astronomical Union catalogs each update, adding more precision to the predictions. Software at NASA's Jet Propulsion Laboratory recalculates trajectories years into the future, testing how sensitive the orbit is to slight changes. A tiny push, an encounter with another asteroid, a gust of radiation pressure, could shift its path entirely. That fragility makes 2025 PN7 a reminder of how delicate cosmic order truly is. It's easy to think of space as static, of planets and moons following fixed eternal paths. But in truth, everything is in motion, influenced by everything else. Gravitational relationships form and dissolve, just like human ones. Companions come and go. Some stay for eons. Others share only a brief orbit before drifting apart. Earth and 2025 PN7 happen to exist in that fleeting middle ground, a relationship lasting decades, not forever. And yet within that brief window, something extraordinary happens. A small rock and a vast planet move together, each tracing its own orbit, each unaware of the other, and still, through pure physics, they align. For half a century, they share the same journey. For 50 years, the cosmos writes a story of companionship, temporary, fragile, and beautiful. What will happen when it ends? When 2083 arrives and the delicate balance tips, sending the asteroid on its next path? Will it wander alone or find another planet to accompany? We may never know. But until then, we have front row seats to one of the most intricate dances gravity has ever composed. A quiet duet between Earth and a stone adrift in sunlight. For now, 2025, PN7 remains there, silent, small, and steady, keeping pace with us as we circle the sun together. Each night it glides through the darkness unseen, a faint point of light among billions, and yet its presence reminds us how dynamic our corner of space truly is. The solar system isn't a static clockwork of fixed paths. It's a living system of shifting relationships. Objects come close, drift apart, return again. Gravity writes its own temporary partnerships, and we are one of them. Earth's second companion will not stay forever. Decades from now, when the quiet forces of the solar system finally pull it away, few people on the surface will notice. The object will fade back into anonymity, just another near-Earth asteroid catalogued and forgotten. But the idea it represents, the notion that even planets can have fleeting companions, will endure. Because in studying this small rock, we glimpse something larger, the constant evolution of cosmic order. Scientists will continue to track 2025 PN7, refining predictions, watching as its orbit slowly unwinds. Perhaps one day it will cross Earth's path again. Perhaps centuries from now, it will drift into another resonance, another dance with another world. These transitions happen quietly, invisibly, yet they shape the architecture of the solar system. Every planet, every moon, every grain of dust is part of that rhythm. For humanity, discoveries like this are more than technical achievements. They are mirrors. They remind us that stability is an illusion, that everything in motion will one day change course. The same physics that keeps 2025 PN7 near Earth will one day separate them. Just as the moon slowly drifts away each year, so too will this companion follow its own destiny. Nothing in the universe stands still. And yet there is beauty in the impermanence. For a few decades in cosmic time, our world shares its orbit with another. A rock no larger than a city block becomes part of Earth's story. It travels with us through light and shadow, through seasons and solstices, through every rotation we make around the sun. We are two travelers on parallel roads, crossing the same invisible bridge in space. When future generations look back at the data, they'll see this moment as a quiet chapter in the history of our planet, a time when Earth had a second companion, not captured, not owned, just moving beside us through the void. It may be gone by 2083, but its lesson will stay, that gravity doesn't only bind, it also allows freedom, resonance, coexistence. The cosmos is full of such brief harmonies. Moons are captured, asteroids pass by, stars tug on each other in long, slow waltzes. Nothing lasts forever, but while it lasts, it is magnificent. 2025 PN7's journey is proof that even in the predictable patterns of orbital mechanics, there is room for coincidence, elegance, and wonder. So tonight, as Earth spins beneath its single visible moon, somewhere out there, a small companion follows, unseen, unheralded, but still with us. It will share our path for years to come, a cosmic echo of our own motion around the sun. And when it finally drifts away, we'll know that for a brief span in time, we were not alone.